solid fluid mixtures over arbitrary topography. We try to model the brick flow as a shallow solid fluid mixture over arbitrary topography, so including the influence of the curvature of the basal surface in the modeling equations. We have used a derived mixture model in the description of a two-layer flow over arbitrary topography, the bottom layer being the mixture model, which I am talking about, and the upper layer being a one constituent fluid. In doing so, we have been motivated by the recent progress in the modeling of shallow gravity-driven flows over arbitrary topography, and which mainly consist in the introduction of curvilinear coordinates adapted to the topography independently by Boucher and Westichenberg and Dettoni and Scotten. The approach initiated by Boucher and Westichenberg was used by our small group in Taiwan to treat several problems related to geophysical flows over arbitrary topography, one of them being that which I am now presenting. Why Boucher and Westichenberg? Because of their powerful matrix decomposition of the field variables and relations, and because the avalanche depth is defined along the normal direction to the basal surface and not in the vertical direction, which would introduce erroneous approximations in stiff topographies. The literature on shallow mixtures is relatively scarce. We found only these 4 papers, and all of them deal with only slightly curved basal surface. Our aim was to account for an arbitrary topography in a sense that will be clearly specified. So a very short overview. First, we introduced the topography-based curvilinear coordinates due to Boucher and Westichenberg. Then we present the modeling equations for a shallow binary mixture, their application to a two-layer flow, and finally we draw the conclusions and show the perspectives. So the bottom topography is modeled as a regular surface in the... you don't? So the bottom topography is modeled as a regular surface in the three-dimensional Euclidean space, given explicitly in Cartesian coordinates. But due to computational reasons, one makes a transformation which relates xy to new parameters, xi1, xi2, on the surface. We may think of xi1, xi2 as being the arc length measured on the curves obtained by intersecting the surface S with the planes x1 equal constant and x2 equal constant. Just a few notations which appear in our formula. N is the unit normal vector to the surface. F is the Jacobian matrix of the transformation. M0 is the metric tensor on the surface. H, the 2 times 2 matrix H, collects the coefficients of the second fundamental form of S. W is the Weingarten matrix, omega the mean curvature. So H, W, and omega are measures of the curvature of the basal surface. Now we have a point P near the basal surface, and Q is orthogonal projection onto this surface. The new coordinates of P are xi1, xi2, the surface parameters of Q, and the distance xi between P and Q. The existence of these new coordinates, which we use for points within the avalanching body, is restricted by this condition, which clearly expresses the meaning of arbitrary topography. The natural basis corresponding to this change of coordinates has the property that the vectors g1, g2 are parallel to the surface, and g3 is equal to the unit normal vector to the surface. Consequently, in the representation of a vector v with respect to this basis, for instance velocity, we can identify a part which is tangent to the topography and one which is normal to the topography. The tangential components of v are collected into this 2 column V, and the normal component is simply denoted by V. Then when representing a symmetric tensor with respect to the same basis, The components referring to G1, G2 are collected into the capital P and T13, T23 in the small p. We use this rule for the extra stress tensors defined here in terms of the stress tensors sigma S, sigma F, and of the constituent pressures PS, PF. S is the solid and F the fluid. So for instance, capital PS contains the normal extra stresses and the shear stress parallel to S, and small ps contains the shear stresses in the normal direction. We are after the mechanical problem. So we have a debris flow which we model as a solid fluid mixture in Truesdell sense. We assume that no erosion and deposition at the base occurs, that the true densities are constant, and that the mixture is a saturated one. Mu denotes the solid volume fraction. So the modeling equations are the mass balance and momentum balance corresponding to each constituent. B is the body force, M plus is the interaction force. The free surface is a material surface with respect to each constituent. At the basal surface, we assume the tangency of the velocity, and on the free surface, the normal pressure is taken to be 0. So we have 10 scalar equations. Correspondingly, we take 10 scalar unknown basic fields, the volume fraction, both velocities, the function f, and the constituent pressures, of which the identification has to be made clear on giving the closure relations for the stress tensors. We may think of PS, PF as independent variables required by the saturation constraint and by the constraint that the two constituents move with the same free surface. Our aim was to simplify this system of equations by accounting for the shallowness of the avalanching mass. More exactly, we wanted to obtain equations for the mean fields of those quantities appearing in these equations, and mean fields which are non-negligible according to our scalings. We have proceeded as follows. First, we introduce non-dimensional quantities with the aid of a typical length L tangent to the topography of the gravitational acceleration and of both true pressure, true densities. Then we have obtained the governing equations in the curvilinear coordinates. For instance, for the solid constituent, we have the mass balance equation, the momentum balance equation parallel to the topography. I recall that V contains the tangential components of the velocity, and the momentum balance equation normal to the topography. J is the Jacobian of the change of coordinates. The divergence operator is with respect to psi psi 2, and the gamma terms are due to the symbol, to the Christoffel symbols. The equation of the free surface is assumed of the form psi equals h. So next h denotes the depth of the avalanche mass measured on the normal to the basal surface. At the next step, we have integrated the mass balance and momentum balance equations parallel to the topography. And the idea was to transform these equations into equations for the depth average fields by using ordering approximations that we have made in terms of an aspect ratio epsilon between a typical length h normal to the topography and the typical length L tangent to the topography, and with the aid of a constant gamma. We assume that the avalanching mass is shallow by taking h of order epsilon, that the tangential velocities are significant, that the solid volume fraction is almost uniform along the avalanching depths, and by these assumptions of bussiness type, we accounted for the non-uniformity of the tangential velocity and of the solid volume fraction along the avalanching depths. We have also some dynamic approximations. I only mentioned that the two constituent pressures are assumed of the order of the hydrostatic pressure, and that the normal extra stresses are negligibly small. In order to go further, we had to assume the constitutive assumption for the interaction force. We have taken this expression, different from that used by Pitman and Ley, and which has been deduced by Schneider and Hutter within a thermodynamic context, but here postulated in an ad hoc manner. How it was deduced, you will see on Friday in the presentation of Professor Hutter. An interesting consequence of this assumption is that both mean pressures are given by the same formula as in the one-component theory. Here, the term AS is the so-called centripetal acceleration, and it shows the influence of the curvature of the basal surface on this pressure. Then we have the equations that we wanted to obtain, and in which one can see by means of H, W, and omega the influence of the curvature of the basal surface, complemented by constitutive equations for these extra stresses, destined for the determination of the mean volume fraction, mean tangential velocities, and avalanche depth H. We close those equations. First, we for the solid constituent, we identify the pressure PS as this normal stress. The shear stresses in the normal direction are assumed negligibly small, so that only these shear stresses survive. For the basal shear stress, we assume the classical Coulomb friction law, and as P bar S, we take one of the three models, that is the inviscid fluid, or a topography adapted version of Iverson and Denlinger model, or a topography adapted version of Savage-Hutter model. Behind this formula is the assumption that the two principal directions of the mean stress tensor are aligned with the principal directions of the mean surface stretching. Three different assumptions on the corresponding eigenvalues differentiate these three models. Here K, K1, K2 are Earth's pressure coefficients. For the Newtonian, for the fluid, for the interstitial fluid, we take the Newtonian or non-Newtonian fluid with small viscosity, so small that only the basal shear stress survives, and this is parameterized by a viscous bottom friction. So this is the complete model of the mixture. Now we have applied the mixture to the description of a two-layer flow. The bottom layer is a debris layer modeled as a solid fluid mixture. The upper layer is a water layer modeled as a one constituent fluid, and as a simplified rough approximation, we assume that the layers are immiscible, so that the layer interface is a material surface for each constituent in the lower layer and for the fluid in the upper layer. The jump of momentum balance equation of the layer interface is written between the solid in the lower layer, the fluid in the upper layer on one hand, and on the other hand between the interstitial fluid and the fluid in the upper layer. The material surface, the free surface is material with respect to the upper layer. The normal pressure is 0. Okay. 2 minutes, 1 minute, and then I finish. So we have followed the same technique as for the mixture model, and we obtain equations that I prefer to show them for the one-dimensional case, just to finish in time and to convince that our equations can be handled. But first, let us introduce the constitutive assumptions. So in the lower layer, we take one of the three models of mixture, and in the upper layer, we take the Newtonian, non-Newtonian fluid, again with small viscosity, so that only the shear stress at the layer interface survives. And this is parameterized by a Chezy-like viscous friction condition. So the one-dimensional case, that is, the basal surface is like a sheet, and all the fields are independent of the transversal direction. The parameter psi1 is the arc length on the curve x3 equals v of x, and the non-zero components of the tangential velocities are taken in the direction of psi1. In the mixture model, we take, as a mixture, we take model 1 or 3, they coincide for this one-dimensional case. And finally, we have the complete set of equations. Depth integrated mass balance, momentum balance, corresponding to the solid, to the fluid constituent, and to the fluid in the upper layer. We recognize here the Coulomb friction, the Chezy-like viscous friction in both equations, the viscous friction for the fluid, the interaction force, and just a final remark, these equations are very similar to those obtained in this paper by some people in Bush's group. The difference between this, our equations and the equations in this paper is that in this paper the lower layer is treated as a mixture in Iverson and Delninger sense. That is, there is only one momentum balance equation because the velocities of the both constituents are assumed to be zero. So thank you very much for your attention.
Any questions?
Chris. So you've got 2 layers, right?
Yeah.
Is it possible that the upper layer, that somehow the solids expand and the upper layer essentially disappears? Does your theory sort of handle that robustly? Can the upper layer get arbitrarily thin?
Yeah, of course. So next we want to introduce the mass exchange at the layer interface. Yeah, this is what we want to do. And to also account for the erosion deposition at the bottom.
Okay.
Actually, we have a theory with erosion deposition at the bottom for 2 layers, but each layer is one component. So now what we want to do is to have erosion deposition at the bottom, but with a mixture. But the problem is to put the jump conditions at the bottom between 2 mixtures. This is what we have in.
Okay, that's all we have time.